Recovery begins as heavy equipment gathers old tires for industrial recycling. From disposal sites, used tires travel toward specialized recycling facilities. Here, millions of old tires await processing. Crumb rubber is now prepared for asphalt modification. Solid meets liquid under heat. Multiple stages ensure cleanliness. Quality control begins with controlled sampling. High temperature stability prevents rutting. Recycled material reaches the job site. Millions of old tires now support modern roads. Every year, millions of worn-out vehicle tires reach the end of their road life. These discarded tires carry years of wear, heat, and mechanical stress. Recovery begins as heavy equipment gathers old tires for industrial recycling. Each truck carries thousands of discarded tires toward a new purpose. Logistics systems move end-of-life tires at massive scale. From disposal sites, used tires travel toward specialized recycling facilities. These facilities are designed to handle millions of discarded tires every year. Each load of old tires is logged, weighed, and documented. Controlled entry ensures traceability of every discarded tire. Here, millions of old tires await processing. Material flow begins at carefully controlled feeding zones. Discarded tires now enter the industrial recycling environment. Human inspection removes foreign debris from worn-out tires. This is the true beginning of transformation. Accumulation belts balance irregular tire supply. Once inside, used tires enter controlled holding zones to regulate industrial flow. Used tires are distributed across multiple processing lines. Queuing systems prevent overload and maintain steady processing. Automated systems monitor volume from end-of-life tires. Human oversight ensures safe handling of discarded tires. Orientation systems prepare used tires for mechanical processing. Final checks ensure only clean, end-of-life tires proceed. From this point onward, waste becomes raw material. Synchronization aligns flow across the factory. Safety systems protect workers and machines. This is where recycling truly begins. Inside the shredding hall, the oldest tires face their first mechanical challenge. Alignment systems steady decades-worn rubber for controlled entry. Human oversight balances force and flow. Scale defines modern tire recycling. Flow remains continuous, even with irregular tire conditions. Hidden structures emerge as worn rubber breaks apart. Inside every worn-out tire, steel reinforcement is finally revealed. All tires lose their form. Years of hardened rubber release stored resistance as heat. No two end-of-life tires fail the same way. What was once waste now advances as recyclable material. Inside this hall, millions of worn-out tires are fed into controlled industrial force. After shredding, material exists as mixed rubber and steel. Uniform spread is critical for effective separation. Powerful magnets target embedded steel reinforcement. Non-magnetic rubber flows onward. Dense bead wire is recovered separately. Recovered steel forms a parallel output stream. Final magnetic passes remove remaining metal traces. Air systems release embedded textile remnants. Each material stream is independently recovered. Rubber is now structurally isolated. Size control prepares rubber for grinding.
Rubber is now ready for refinement.
From separation to precision grinding. Feed rate determines granule quality. Granulation systems prepare rubber for precision refinement. Cutting replaces tearing. Rubber shape begins to normalize. Energy input is carefully controlled. Screens define acceptable granule dimensions. Out-of-spec material is reprocessed. Uniform black granules signal readiness for finer processing. Air systems protect quality and safety. Even distribution is essential for precision milling. Here, granules become crumb. Granules now enter the precision stage of refinement. Extreme cold prepares rubber for clean fracture. Cryogenic cooling alters rubber behavior. Prepared material enters fine grinding. gas is removed, material remains. Uniform particles ensure predictable asphalt performance. Classification defines final specification. Out-of-range material is refined again. Uniformity is achieved.
Every parameter is verified before transfer.
Crumb rubber is now prepared for asphalt modification. Clean transfer preserves material quality.
Before blending, crumb rubber is visually inspected for consistency.
Rubber is introduced with precision. This vessel drives transformation. Solid meets liquid under heat. Shear energy activates the rubber. Heat allows rubber polymers to expand. Time completes the reaction. Byproducts are safely managed. Specialized pumps move material that no longer behaves like liquid asphalt. As rubber activates, viscosity rises and flow resistance increases. Temperature control keeps rubber polymers active. Continuous agitation preserves homogeneity. Elastic behavior confirms full rubber activation. Blending is complete. Thermal vapors are removed without material loss. The binder now moves toward final conditioning. Conditioning begins by stabilizing flow. Homogenization prevents separation before filtration. Flow control maintains uniform conditions. Pressure confirms filter performance. Multiple stages ensure cleanliness. Filtration removes residual irregularities. Safety systems protect continuous operation. Stability tanks preserve uniformity. Gentle motion prevents separation. Pressure stability confirms effective filtration without blockage. Fine filtration removes remaining inconsistencies.
Bypass systems protect continuous production.
Gentle agitation preserves phase stability.
Precise temperature control sustains binder performance.
Quality control begins with controlled sampling. Every batch remains fully traceable. Testing occurs under controlled laboratory conditions.
Viscosity defines how asphalt flows.
Flow resistance is precisely measured.
Elastic behavior must withstand traffic stress.
Shear testing simulates real road loads.
High temperature stability prevents rutting. Cold resistance reduces cracking.
Elastic recovery confirms rubber performance.
Uniformity must remain over time.
Performance metrics align with standards. The binder meets engineering standards.
Testing complete. Deployment begins.
Approved binder is stored under controlled conditions. Distribution begins at the loading bay. Each shipment is measured and controlled.
Material moves toward real-world use.
Recycled material reaches the job site. The binder joins stone and aggregate. The road material takes final form. The material is placed with controlled precision. Compaction defines durability. Performance begins at the surface. Waste becomes infrastructure. Millions of old tires now support modern roads. And this is how modern factories turn old tires into durable roads from start to finish.